So my name is Semantic, and I'll show some results that we achieved on the project. So overall, it's a European project that started in 2009, so in the last year now, and started the fourth year. We have six partners, and we actually have in Bremen now part of Munich University. All of the partners work on different aspects of the global vision, which is building a worldwide web that can be used by and skilled by robots. So personally, I prefer to have a bit of a bigger robots, so it's kind of describes a bit better what we're actually doing. So the worldwide web is large, but what we're targeting at the knowledge that can be killed by robots and that can autonomously be used by robots. And in particular, we're looking at information about actions, tasks, descriptions that can download and execute, information about environments, so formal descriptions of the environment, configuration, objects, and so on, and object models that robots can use to recognize these objects and to reason about them. And yeah, so the different partners work in different aspects of the vision, some more on the perception side, some more on the learning or action execution part or this web-based database. And our job is the representation language that we use to describe this information. And yeah, so I'm also a bit biased probably on this aspect. But since the project is about the knowledge base in the web, I think it's also an important aspect of the whole thing. So knowledge exchange over the internet has been very popular and successful among humans. And humans use it a lot to tell other people how to do stuff. So for example, on pages like WikiHow, you find instructions how to set a table, how to clean an apartment. You have websites with cooking recipes and so on. And humans, of course, describe it in natural language, often in English. But if you want to download and execute these things, you need a lot of common sense knowledge. So you can't just execute an cooking recipe. You need to interpret it. You need to find the ingredients. You need to understand what is actually meant. And one of the big challenges that we're facing over Earth is how to equip robots with this common sense knowledge that they need in order to really understand these download instructions. So, four of the key questions that we need to answer is first, for the robot that is to upload information, which information is actually worth to be exported. So which of the information that a robot has could be useful to a different robot, and that also includes to make this information explicit. So if it's just available in some variable in C or so, the robot doesn't really know which information it has. So we need to create explicit representations of this knowledge that can then be exported and described. The second important aspect is how to describe this information in an unambiguous way that another robot with a different hardware configuration in a different environment with different sensing capabilities can actually make use of that. So it's by far not enough to just dump some data structures and replay them, but we really have to have very crisp semantic descriptions there. On the downloading side, it's a problem of how to find information. So the robot is then in front of this database, needs to explain what do I actually need, and based on the results, it has to decide which ones are usable by this robot with this configuration, and how do they need to be adapted, or which additional information is maybe needed to use something. So for executing a task, do you maybe need some more object models to recognize the objects that are involved in something. And the final part, how to execute this. So if we have a very abstract task descriptions that we exchange, we need to translate them into really concrete calls to the controllers on the robot. So we need to ground it in the actual environment the robot is in. And that's another big challenge that needs to be overcome. So in Mobile Earth, we're having on one hand a cloud-based database, and on the other hand, we have a local system that is running on the robot. And both of them are communicating via web service interface. And using this interface, the robot can then send semantic queries to this knowledge base on the web and receive the results. The main kinds of information, as I mentioned, are action recipes, so task descriptions, models of objects that can be used to recognize these objects, and that also describe some semantic properties of them. and environment maps that describe, for example, a two-dimensional map of the occupancy grids, or three-dimensional semantic maps that contain objects in the environment. And you're seeing that all of these things are described as puzzle pieces, and that means that each piece of information in the knowledge base is annotated with some meta information, and that describes basically which capabilities the robot needs to have in order to really use this information. That can be, for example, for actions that you need like a gripper or some object recognition capability, or that you need a certain program in order to load an object recognition model and really interpret this to execute this, to recognize this object in the environment. And all of the robots are equipped with like a kinematic and semantic model of themselves, so they are aware of their own capabilities, of the software they have, and of the hardware components they have. And there are methods for automatically matching these puzzle pieces with a semantic model to find out what are the differences. That's very important. It's like the equivalent of a Google query. So if you ask something to Google, you write in a search query that explains what you would like to have, and you get a bunch of results back. You filter out those that you don't understand because they're maybe in a different language, because they don't fit to your capabilities. And then you're selecting among the results which is the most likely that helps you in a concrete situation. And by having this matching between the requirements and the capabilities, we're trying to replicate this on the robot system and let them autonomously use this online resource. So the information or the control flow for downloading something is about like the following. So if the robot is given a novel task in a novel environment, it's first checking if it has environment maps. If not, it's trying to download them based on the address of the environment. Then it checks if it has an action recipe in its knowledge base that can be used to solve that specific task. If it is the case, then it's generating a robot plan and trying to execute this. If there's no action recipe yet, it's sending this request to over Earth, performing this capability matching to see if all components are available. If not, it's iterating further and trying to download all of these components from Google Earth, and then it's automatically sending them to the correct path on the robot. So for example, if it's downloading an object model, it's automatically sending it to the respective vision component to then execute, be able to recognize that object. I think I'm going to skip that video. So that's a description, an example of an action recipe. So we have sequences or partially ordered task descriptions. They can be composed in a hierarchy. So for example, this grasping a bottle action can be decomposed into reaching towards the torch pose, opening the gripper, and so on. And each of these actions can have additional properties like the object acted on or the true location. These are described in OWL, it's a language for the semantic web, and it has logical interpretations, so the robot can reason about that and use it in its knowledge base. This OWL language is then on the robot translated into a plan. So it's a language for task execution, and it's optimized for robust execution of concurrent reactive behavior. So you see that this sequence of action is here translated into a set of goals that are to be achieved in a certain way. So the environment description that we have consists of different levels of abstraction. So on the one hand, we have spatial information, which can be positions of objects. It can be free space and occupied spaces, so we support different kinds of maps. Each of these objects can be annotated with different semantic information, like this block here is a refrigerator, is composed of certain parts, has some dimensions and so on. And all of these set these objects into relation. In order to find objects in the environment, as I mentioned, we use the address of the environment that is used to formulate the search query. And each environment, like one room, for example, can be described by different kinds of maps of specific types, and the system then knows which types provide which kind of information. So here I show a video of a demonstrator that we had. So we had two different robots, and both of them performed the same task based on the same action recipe in two different environments. So they downloaded all the information they needed. So the action description, the environment map that contains the object instances or instance of some of the objects, They downloaded the recognition models and used that to serve a drink to a patient in bed. And for example, here, this drink was inside a cabinet, and the first robot, here or here too, had the ability to estimate the articulation properties of the cabinet. So it learned how to open it, and then associated that information with the object model. And the other robot in a different environment could download this. The same cabinet was there, but it was a different environment configuration. And so it could use that to recognize that object and to update this information. So here you see the tier 2 is navigating based on the downloaded occupancy grid map, putting the handle to estimate the articulation properties, and here it's grasping the object based on the downloaded object model. And yeah, the patient is not physically there. And you'll see it uploading the models to RoboEarth. And the Amigo in a different location is then going there. So here this learned articulation model that has been associated with the cabinet model. And this Amigo robot doesn't have force sensors and it's not compliant, so it really needed this information about the articulation to be able to open the cabinet. And here we have a real patient. Okay. So to conclude, four of the main questions in our project are which information to export, how to describe it in a way that other robots can make use of it, how to find information in this knowledge base, how to really ground it then in the execution. And our approach is we focus on action recipes, object models, and environment maps for the execution. We use an OWL-based language that can be described. It can be used to describe all this information in a formal format. We have this capability matching for selecting information for the knowledge base and translate it into robot plans for the execution. And tomorrow morning we have a tutorial on another aspect of the RoboEarth project. What I explained was the knowledge sharing aspect. The RoboEarth Cloud Engine is about executing programs in the cloud, so that we can't just upload information and download it, but we can also send requests to do some computation online and then get the results back. And that's going to be a hands-on tutorial tomorrow morning, 8:30 to 10:30 in 2 over there. Thank you.
Thank you very much. I mean, I thought the topic of this event was just really fantastic. So I want to start. I was thinking about what to put as a title for this presentation, and I think I'm a really big fan of crowdsourcing and what they call as the human computation. And I think more and more, this is just my. You can sort of help me accountable for this sentence, but I think we'll see much more. Work towards human computation in robotics over the next years. Like there will be a Louis von Ahn of robotics. Louis von Ahn is the Okay. So in this talk, I'm going to talk about the Kinect at Home project, in which we try to build 3D models from all around the world. And so it's sort of I was having this kind of influences from the human computation work that other people in computer science are doing, and then I was bringing things together. So the motivation for this is that in robotics and computer vision, as I think I don't have to stress this too much, but we need lots and lots and lots of data, especially for quite big applications like 3D construction, modeling, object detection, semantic mapping, mobile manipulation, and so on. And I myself gone through the agony of collecting data sets for various papers, and that was very, very painful to get like data from various environments, like say lots of kitchens, lots of living rooms. Like we always talk about robots in living rooms, robots and so on and so forth. But in my lab as well, we built this kitchen in the lab, and that's the only kitchen that we worked with, which I thought maybe we could do something with that. So the question that, or one of the questions that I had while doing the project is, what would a mobile mobile robot faced with if we were to ship them today at home? Like we are like say that we have this dishwashing robot that can also do cleaning and so on. And what would it see? What would be the kind of images that it would get as we do this thing? And then the Kinect at Home project started sort of as a pet project in the lab, where I tried to recruit lots of people in the lab, which I was not successful at all because everyone has their own stuff. But then this is the work of me and the undergraduate student. And yeah, the problem, as we said it, is that data collected from mock environments can lead to optimistic evaluation results. And can we do something better? And the challenge here is that we can't simply use Google Images or Flickr and so on for this kind of thing because of various reasons. 3D is important for us. These are 3D like embodied agents. We might require a sequence of images, not just one snapshot of this countertop, but how does it look as you approach it, which is what a robot would see, and the diversity of this. So the solution or the approach that we came up with for this is that the Kinect sensor is very popular, is the fastest selling consumer electronics device in history, and can we make it that simple to connect data and send us for regular people, send that data to us, and can we make it interesting? This is sort of a unique time. It's as if like every robot has 5 Kinects on top of it, and millions of people have one in their living rooms. That's like millions of people having 6 scanners in their living rooms. Like that never happened before, really. So what can we do with it? And what we came up with is that we built this web service where you can go onto the website, you can record the Kinect video directly in the browser, and then hit record, you record whatever you want to model, 3D model for. And then the website or the servers goes off and they do their own thing and build a 3D model, and then we can see it just like that back in the browser, just like a YouTube clip, like you are uploading a YouTube clip. So then you have your gallery of 3D models and so on and so forth, and also you can embed these 3D models into other web pages, just like a YouTube video as well. You can see this, so that it's attractive to regular people. So I'll just play like a short video on how this whole thing works. So you go on the website, you install this browser plugin that we developed, which I'm going to talk about in a bit. And then that's in the browser, that's Chrome. So you plug your Kinect in or your Asus camera or whatever. And then there's a record button, which you're not seeing now. And then you just record whatever you are trying to model. And then that data is at the same time uploaded to our servers. When I say our servers, that sounds like something fancy. It's just the desktop on my desk, actually. It's sent to. And then we have the data. And then that machine then goes on to build the 3D map, and then build the mesh, and then everything, all that. And then it gets displayed back to the user in the browser. So we call that Kinect at Home and so on. So in this case, yeah, for example, this was some 20 megabytes of recording. So that's the basic thing, right? As I talked about, and I think I will quote some more. So that's the very simplified pipeline where there's this compressed RGBD stream. That's one of the challenges that that I saw starting to do this, because apparently there are lots of RGB codecs, like video codecs, but there is none RGBD. There's not an RGBD codec, which then we tried to. We ended up making one basically in order to solve this, because no one is going to wait to upload gigabytes of data. I mean, you can't really convince normal people to do that, even if it means having robots or whatever. And then the jobs are sent to a job queue. We are using the 0NQ transport library for that, which is quite handy. It's quite useful. And then it's sent to lots of, now we have two, before it was one, mapping servers based on their loads and so on. If one is busy, it's and the other and so on. So that's quickly the pipeline in more detail. When the video is received, it's being unpacked, and then we track the poses for each frame in this recording, and then we build. And that part is I said it as the fun part because that's also an actively researched area, which we are also doing quite a lot in the lab, and that's the sort of thing that gets us going here. And then we build the mesh, we build the pictures and everything, and then we upload it. So we launched it, and then so far we got some 600K page views, about 1,000 Kinect recordings, and it's being uploaded like every day or every week and so on still. And then we are continually updating this and so on. We got some attention from media. This was quite funny, talking evening news about this. So the results. You must be wondering, okay, how does this work? So here's this. Here's one of the articles. This is from Wired. That in this case, the reporter himself tried the service, and then they actually embedded this 3D model into the article. So this is served from my desktop. This little bit here, just like the YouTube video. So that in this case, they tried to model their workshop. Okay, and then just to show you some variety of so that's the whole model, and this is what you get when you open this. When you go to your page, that's okay. You get this model. There's another. There's a kitchen. You can see that there are like problems, and obviously these kind of data, we get lots of very challenging videos because these people have no clue about computer vision or robotics or anything. They just want to swing this camera a little bit, and they expect the best. And we got really weird recordings that we just don't get if you want to record some data set yourself, because you know what are the weak points of your algorithm and so on. You try to, even when you are nasty, you try to be not so much nasty. And so yeah, we got lots of recordings. And so here's someone's kitchen, and also we are, as I said, improving the tracking, the mapping on the old time. So this is an old version. This is a model built with the old version of pipeline where we're not doing this one. And this is with the new version where things are more crisp and so on. It's the same model. So if I zoom in, you'll see that. Here's someone's fireplace, someone's workshop, I think. Desk, computer screen. So yeah, so this is someone's table with the old pipeline, and now that's with the new pipeline that we keep building on. So you can see that if you get more accurate poses, then you go from this to this. So yeah, I think this is also the old one. Here and compare. This is the sort of the new one. Yeah, we also got some strange things like yeah, I don't know what it is, but yeah. They were actually robotics researchers. So someone's some people posing. Yes. We got people who are modeling themselves in order to put them into games and so on. So they then make articulated body models. And we got lots of weird applications that people are using. Some industrial designers are using it to showcase their objects that they design on the web. Yeah, so that's about it. So these are just a selection of. I don't think I have much time left, so I will not talk about these things. But that's the sort of the detail on how we do the reconstruction, how we do the actual mapping. And I will just say very briefly that we have we combine lots of different approaches like depth, ICB, visual, RGB feature tracking, and so on. And then in the end we have the loop closing step, which is we are trying to write the yeah, so that's about it. We are in the middle of releasing all this data for everyone to use and so on, and we are sort of annotating it with hard videos or easy ones and so on. And we also have an annotation mechanism in the back where you can annotate the videos for objects, and you can just send a link to everyone. It's also browser-based, or you can send it off to the mechanical turret or something, and then we will be able to use that. So I'm really curious about somehow wrapping this up with Raptuya, with the Robo-Earth engine. I think yeah. And yeah, so that's the.
So I hope to see it beyond the board.
Yeah, exactly.
One quick question while we switch over. Anyone?
Is part of the idea that if you have all these kitchens, say for example, filmed in the wild, so then your robot can generate some kind of a generic prototype of a kitchen, so that when it goes off to a new kitchen, it will be able to be familiar with this new kitchen?
Exactly. That was actually the original idea with it. But then it turned out to be a bit optimistic, as researchers tend to do. Probably. But that's still the idea. And I think now I see this as just the first step in, first kind of experiment in playing with this kind of cloud robotics things. And these are our experiences.